Hello, 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 So guys, the last session, I solved this some Fourier series of simple function. As you see further, we will solve the Fourier series problem with some physical phenomena like spring mass system or some, and also I will cover the precedence condition of the Fourier series. So let's take one example. A periodic forcing. Let's consider a periodic forcing function acts as a spring acts as a spring mass system. Like um, this is given like this is one axis and it is working like okay. So this period is 2. This is also 2 and this is also 2 and this period is also 2. So we consider one function like this is acts like a spring mass function, like a particle is moving here to here, it is coming to backward to this direction, like that. So the question is find a sine series representation y considering the function to be odd and one cosine series y considering the function even. Okay, so how we will, so this is our question. A periodic function we are considering like that, and sorry, this should not be like that, this should be like that. Okay, so how we will solve it, let's see. uh, if this t equal to 0 location we select, like if we select some location at t equal to 0, then this will be our function. So this will be minus 2 and this will be 2 and this will be also uh, 0, 2, 4, 6, like that. So so t equal to 0, so the function first we consider one function f is equal to minus 2 to 2 when t is greater than minus 2 and less than 0, and it will be 2 when t is less than 2 and greater than 0. Okay, so like that. So this is minus 2, this is plus 2. So this will be minus 2, this will be 0, 2, 4, like that. So uh, this will be our odd function, while to consider a even function, uh, and we know for the for this odd function an will be 0. Okay, so this we will get from the last experience which we solved the last eight thing. So whichever the left is bn. Okay, so bn we can define 2 by t, 0 to t, f1x, f1, sorry, not x, you can say t or x, so whichever the function you consider, sine n pi t upon capital T dt, where n equal to 1, 2, comma 3. Okay, so how we will solve? Our period is 2. Yeah, okay, so is total 4, so t is equal to 2, 2t is equal to 4. So this will be 2 by 2 divide 0 to 2, 2 sine n pi t over 2 dt. Okay, so if you integrate this, you will get 2. Okay, and from here you will get cos n pi t divided by t and divided by this term, so it will become 4 by n pi. Okay, so here we will get limit from 0 to 2. So you will find 4 by n pi and cos n pi t by 2. So you when you put this limit, you will get cos n pi minus 1. Okay, so is our this is our Fourier series of f1. So Fourier series then again, like this cos n pi, we know it is minus 1 to the power n. Okay, so if we substitute this minus 4 y n pi, sorry, the Fourier series of this function fl of t can be written summation from n 0 to infinite 4. From here you can write 1 minus minus 1 to the power n upon n pi sine n pi t over t. Okay, so if you expand this in terms of, then you can write 8y pi sine pi t by 2 minus 8y 3 pi sine 3 pi t by 2 plus so on. Okay, so now if we select the t equal to 0 location, now if we select t equal to 0 position, what we will get? So sorry, if we select t equal to 0 for odd function, oh, sorry, for even function, because we have solved for odd function, so now we our aim is to solve even function. Okay, so for even function, how we will write, like f to t we consider. So now it will be for odd function it we will consider like that. So this is our t equal to 0. Okay, so now it will be 1, this will be minus 1, and this will be 3, and this will be minus 3. Okay, so how can we write this even function? Even function we can write minus 2, 2, and again minus 2. Okay, so this this minus 2 will be till um, here to here. Okay, uh, this will be here, this will be minus 2, this will be plus 2. So minus 2 to 1. Okay, so minus 2, sorry, this is plus 2. So plus 2, from here we can write minus 2 to minus 1, it will be minus 2. Then from here to here it will be 2, from here to here. So it will be less than 1, greater than minus 1. And from again from 1 to 2 it will be minus 2. So minus uh, sorry 1 to 2 it will be again minus 2. Okay, so now how we will write the function Fourier series of this function. So this is again one trick which is called like if even function is there, then our Vn will be 0. Okay, you can note down this good trick. So the function can be written like an can be written like 2 by t integration from 0 to t f to t cos n pi t by capital T dt. Okay, so for this you can say 2 by 2 0 to 2 2 cos n pi t over t. Okay, dt. And from 0 to 2 uh, 0 to t, so we can break it in 0 to 1, then 1 to 2. Okay, so 1 to 2 in minus 2 and cos n pi t over t dt. Okay, so you can solve this integration easily. By 4 we will get 4 by n pi sin n pi t over t limit 0 to 1 minus 4 by n pi sin n pi t over 2 from 1 to 2. Okay, it will go 8 by n pi sin n pi by 2. Okay, so now when n equal to 0, for n equal to 0 we will get 0 a0 equal to 2 I t 0 to t f to t dt. Okay, so for that we will get a0, this is 2 by 2 0 to 2 sine n pi t by, sorry, this function is will be 2. Okay, so we break the limit 0 to 1, it will be 2 dt, and 1 to 2 it will be minus 2 dt. Okay, so it will be cancel out, not directly, but you can solve it. This will be 2 1 minus 0 plus minus 2, it will be 2 minus 1. Okay, so it will be 2 minus 2 equal to 0. Okay, so the Fourier series then will be for f to t, it will be summation n equal to 1 to infinite 8 by n pi sin n pi by 2 cos n pi t by 2. Okay, so uh, this will be the series. So next question we will go to the extension of this question, like uh, how we will determine. So the next question is for this force which is acting the same force which we considered before for the spring mass system. So we have to determine the steady state response of this forcing function. Okay, so we have to find the steady state. So we have seen the coefficient of this Fourier series of an odd function which we considered before, just in our question. So we found a zero, sorry, a n is equal to 0 and vn is equal to this is 2 by 1, 0 to 1, 100 sine n pi t over t dt. So actually we get it like the amplitude is 2. So instead of this is 100. So we are getting from that this 100, and after that you can solve this form minus 200 to have it upon n pi cos n pi t 0 to 1. So you got minus 200 by n pi cos n pi minus 1. Okay, so like this is giving like um, this is our base. So this is the spring, and this spring is connected, and the spring constant is 100 Newton per meter. So this is 10 kg block, uh, and this is 0.5 kg per second. Okay, to this up. Okay, so now the Fourier representation of this function. So Fourier representation, we got ft is equal to summation n equal to 0 to infinite, sorry, n equal to 1 to infinite, 200 by n pi 1 minus cos n pi minus, sorry, cos n pi sin n pi t. So it is 400 by pi sin pi t minus 400 by 3 pi sin 3 pi t. Okay, and so on. Uh, so the differential equation, if you get from here, 10 dy over dt square plus 0.5 dy over dt plus 1000 by it will be equal to this function ft. Okay, actually this differential equation we can get from this figure, as you have studied in first order differential equation. So because of this differential equation is linear, we can first find the particular solution by p uh, corresponding to the first term in the right, which is in this ft, which is this one and this one, and corresponding to this, so we will call it by p1, and corresponding to the first term on the right hand, then it will be by p2 corresponding to the second term of, so the finally steady state solution you will get by p of t equal to by p1 plus by p2 plus dot dot dot. So doing this for the three terms, like we will go up to three terms. So what we will get, so by p1 we will get 0.41 141 sine pi t minus 2.5 into 10 to the power minus 4 cos pi t. How you will get this? You simply consider this is as a phi x, and for this differential equation you can find yh, the homogeneous part. Then you consider phi x is equal to this one. So for two methods are there. One is from undeterminate coefficient method, and another one which I have also explained. You just this is sine term, so you can consider a sine x plus b sine b cos x, and then you can solve from this coefficient determinant method, and you will get this a and b term in terms of um, this function. So here it is number, so you will get some number. Okay, so similarly you will find by p2 and by p3. Okay, so similar function in terms of sine 3t, this will be some constant like 0.376, and here you will get 1.56 multiplied with 10 to the power minus 3 cos 3 pi t, and similarly here you will get sine 5t and cos 5t term. Okay, so actually this, rather than solving the problem each time for the each term, we would have find a general function by p at a function n. Okay, so corresponding to the term you will get 200 y and pi and cos n pi minus 1 sin n pi t. Okay, so as a general function of this n, so whatever you will get the n equal to 1 is corresponding to by p1 and this like that. Okay, so note the amplitude of this sine term in by p2 is obviously dominate the solution as displayed, as you can see here, this will be output will looks like that. Okay, and it looks like that. So like our function is like that, but this by pt will looking like that. Okay, so what, like again, this will be this by p2 is the angular frequency of 3 pi radian per second. Okay, So the frequency of this input frequency was pi radian per second, and this happens because this natural frequency of the undamped system was 10 radian per second. Every close to this frequency of the second sine term in the Fourier series expansion. Hence, it is this overterm that resonate with the system and not the fundamental. So overtone may dominate the steady-state response for any undamped system that is forced with the periodic function having a frequency smaller than the natural frequency of the system. Okay, so this overshoot can be happens. This is also known the Gibbs phenomena. So what is the Gibbs phenomena? Gibbs phenomena is like if your system is discontinuous at the age but continuous in this periodic function. So this is the initial condition for the Fourier series transformation. So the Gibbs phenomena is this will go this overshoot like that, and then at the end it will be undamped like that. So this overshoot of this corresponding to this function, this overshoot is known as the Gibbs phenomena in this Fourier series. So as this number of terms in Fourier series increases, this overshoot will decrease. Like you can see on the internet also, like if we have some square shape. Okay, and if you will take this number of terms around 25, this will go like that. So this square term will looking like that. Sorry. um, so due to this Gibbs phenomena, this square term will looking like that. But if you increase this number, n is equal to like let's say 125, this will converge like this converge will be converged like this. So this overshoot will decrease. So this is the Gibbs phenomena. So number of terms, but whatever you will take, at least 9% of this maximum height overshoot will remains as such. So this is something called Gibbs phenomena in this Fourier series. Next, we will move on the pleasurable, pleasurable identity. We take one example. So let's say it is called perceivable identity. Okay, so just assume the Fourier series corresponding function fx which converges to fx in minus L to L periodicity. So what will be the Parseval's identity. So Parseval identity will be 1 by L minus L to L. If we integrate the square of this fx with respect to x, then we will get y2 plus summation n equal to 1 to infinite an square plus bn square. Okay, so we have to prove this first. How we will prove? So let's say the Fourier transform Fourier series of this fx is epsilon naught by 2 plus summation n equal to 1 to infinite and an cos n pi x but a l, where l is the here it is given the periodicity, uh, plus vn sine n pi x by l. So let's say this is the Fourier series of this function. So the integration of this function, uh, sorry, now we will multiply this function, this fx by fx. So our fx square will be a0, sorry, a0 by 2 f of x plus summation n equal to 1 to infinite an fx cos n pi x by l plus bn fx sin n pi x by l. So now integrate this to get this identity. So we integrate this minus L to L fx mod square dx is equal to, this will be a naught by 2 integration minus L to L fx dx. Okay, so minus L to L fx dx plus summation n equal to 1 to infinity an integration minus L to L and fx cos n pi x by L plus Vn f integration fx sin n pi x by L, like that. So what will be the value of this one? This like we know that a0 is 1 by L minus L to L fx and dx. So integration of minus L to L f of x dx will be a naught into L. So here you can it will be 2. Sorry, if we consider a0, but when we consider this function, then it will be 1. Okay, so now you can write this instead of this function. So similarly, when you solving this, so you know that this is the an, right? An into L, and this is the Bn into L. So you can easily write minus L to L fx whole square dx will be a naught square by 2, sorry, this value of a naught plus summation n equal to 1 to infinite and an, and this integration is equal to an plus bn, and this integration will be equal to bn into L, and this will be a into L. So this L will be common and go to this side, and it will come minus L to L fx whole square dx is equal to a naught square by 2 plus summation n equal to 1 to infinite an square plus bn square. Okay, so this exists as a Parseval identity. So Parseval's identity corresponding to this Fourier series you can also find for the any Fourier series. Like if you know an and bn and a0 value from the quotient of this Fourier series, then you can find this. Okay, so like for example, if we take One example, fx is equal to x. Fx is equal to x for the periodicity 2 minus 2 to 2. Okay, then what we will get from the previous class also, we got a0 equal to 2 from here, and you will find an equal to 4y n square pi square cos n pi minus 1 when n is not equal to 0 and vn equal to 0 for the even function, which is, sorry, x square fs. So for even function, this bn will be 0 and an will get this, uh, we got this. So now preservable identity, you can say 1 by 2 because L 2L is equal to 4, so L is equal to 2. So 1 by 2 integration from minus L to L, fx is fx square. mm, this is, Here we have this one. So for odd function bn is 0 and this is, so 1 by 2 minus L to L, uh, fx square, so our fx is x, so we will find x square dx, it will be equal to 1 by 2, uh, you can directly write a naught, so a naught is 2, so 2 square by 2 plus summation n equal to 1 to infinite, an is this one, so this will get 16 square, so n to the power 4 pi to the power 4, and it will cos n pi minus 1 the whole square. Okay, so you will get this relation from here. you, you are getting this right. So from here you can write, like this is our 2 to the power 4, 4 by 2, this is 4, and if you integrate this from minus 2 to 2, what you will get, 1 by 2, x cube by 3, so here is 4, so this is something is, sorry, 1 by 3 minus 2 to 2, so 1 by 6, and it will go to 8 minus, minus 2 to minus 8 plus 8, so it will go to 16, and here it is 4 to the power 4, sorry, 2 plus summation n to the power 1 to infinite, and it will be 16 n to the power 4 pi to the power 4, and cos n pi is minus 1 to the power n minus 1. Okay, so if you subtract this, see, 2, so 2 यहाँ से 4 4 8, 8 by 3 equal to 2 plus, you can write this, 16 y pi to the power 4, and you can write from n to infinity like, 1 to the power 4 plus 1 by 3 to the power 4 plus 1 by 5 to the power 4, like that. So you can find any fraction in terms of series from this possible uh, identity, right? Okay, so what is next? Next is, we take one another uh, example for the Fourier series. So let's solve one bounded value problem with the help of this Fourier series. So boundary value problem with the help or using Fourier series. You can say Fourier series application in boundary value problem. Okay, so how you will solve? Like let's take one question. For example, we have derivative u over derivative t equal to 2 derivative square u over derivative t square derivative x square. Sorry, take x. Then u 0 comma t equal to 10 and u 3 comma t equal to 40 and u x comma 0 is 25. Okay, where u x comma t mod is less than m. Okay, we write here this is the derivative of t and here is derivative of space. So space and time both derivative are there, and this is one uh, problem. So to solve the this present problem, uh, we assume that this ux comma t will be the function vx comma t plus psi x. So where this psi x is the suitably determined in terms of vx comma t. The boundary value problem then become if you put this into this, so this will be der v over der t equal to 2 der square v over der x square plus 2 psi double dash x. Okay, and this constant will be v 0 comma t plus psi 0. This will be 10 and this v 3 comma t plus psi 3, it will be 40. Okay, and this vx comma 0, this will become plus psi x, it will become 25. Okay, this can be simplified by choosing, if we choose psi double dash x is equal to 0, then our psi 0 is equal to 10 and psi 3 equal to 40. What is the meaning to consider this? Uh, so if you will find this psi 0, then you can easily solve taylor v over taylor t equal to 2 taylor square v over taylor x square. um, this will become v 0 comma t equal to 0 and v 3 comma t equal to 0, and this 40 and this will go out. So and v x comma 0 will be 15 minus 10 x. Why we do this? We just do this to shift the origin from here to here, because in this boundary value problem there are some numbers. So this is equal to 0 at the boundary point. So just we shift the uh, coordinates. Okay, so mm, like why if this is, if you solve this from here you can find 5x is equal to 10x plus 10. Okay, so you can easily find this bx comma t equal to, you can solve this heat equation as a boundary value, simple boundary value problem. So bxt will come out psi equal to m equal to 1 to infinite, and Vm e to the power minus 2 to m square pi square t by 9 sine m pi x by 8. Okay, so if you consider this thing, you will get 15 minus 10x is equal to summation m equal to 1 to infinite Vm sine mx pi upon 3. Okay, so if you solve from these two conditions, you know from the Fourier series this Bm will be 2 by 3 from 0 to 3, 15 minus 10x, which is our fx. Okay, so 10x, then it will be sine m pi x by 3 dx. Okay, so you will get from here 30 upon m pi and cos m pi minus 1. Okay, so now you can say like ux comma t we considered vx comma t plus psi x. Okay, so what will be ux comma t? You just put bx e psi x, which come 10x plus 10 in above step, and here you can write m equal to 1 to infinite 30 by m pi and cos m pi minus 1 and e to the power minus 2m square, and all this term will come where uh, what is this one? This is for bm. So we easily find this type of constant with Fourier series by comparing this series. Okay, so this is some one way to solve the differential equation, boundary value differential equation. If you did not use this type of thing, then it is difficult to find here this Vm. Okay, so it is important application to solve in boundary value problem. The from series, sorry, this Fourier series application is solving the boundary value problem. Okay, so next we come on Fourier integral. We we will come on this Fourier integral in next session also. But I would like to just summarize some condition like how we will find and what will be the need of this Fourier integral. So we considered the theory and application involving the expansion of a function f(x) of a period 2L. Okay, so into the Fourier series. So one question which arises quite naturally, if you think, is that what happened in the case VML tends to infinite. Okay, so from the above we are considering some periodic function from 12. So we are considering a periodic function in a finite range like L2 minus L. But what will happen if this periodic city goes to infinite, right? Uh, in other words, we say this L tends to infinite. Okay, so what we will sell? So we shall find here that in such case, this Fourier series, uh, this Fourier series will become the Fourier integral. Okay, so the Fourier integral is like first thing, the need of this Fourier integral is like that. If you ask some question like uh, what will be if this L go to infinite in this previous Fourier series. So for the Fourier integral, First, we consider that fx and f dash x, both these functions are piecewise. Okay, piecewise continuous in every finite interval. Okay, the second thing, we consider minus infinite to infinite. This f mod fx dx should be converse. Okay, this should be not diverging, this integral. Okay, so this fx is absolute integral. You also can use this absolutely integrable in minus infinite to infinite. Okay, so then this Fourier series, this Fourier integral theorem is called that fx will be 0 to infinite a alpha cos a alpha, yeah, ax plus b alpha sin alpha x. Sorry, this is alpha x and d alpha. Okay, so what will be the a alpha? This a alpha will be 1 upon pi 0 to minus infinity to infinity fx cos alpha x dx. Okay, and the another coefficient b alpha will be 1 upon pi minus infinity to infinity fx sin alpha x d alpha, sorry, dx. Okay, so this result 1 holds if this x is point of continuity of fx. Okay, so if x is point of discontinuity, we must replace this fx by fx plus 0 plus fx minus 0 upon 2. Okay, so as in this case of Fourier series, note that the above conditions are sufficient but not necessary. Okay, the similarity of this uh, 1, this is 1 and this is 2. Okay, with corresponding results for Fourier series is apparent. The right hand side of this 1 here, sorry, here, uh, one is something called the Fourier integral expansion of fx. Okay, so some another forms are also there for Fourier transform integral that we will discuss in the next session. So thank you for this session.